It is now possible that we can control the effects of corrosion noise very efficiently using electronic means which have been developed by NASA and are available to us through our members in Italy, a company called Subrel. This can only be monitored using the Alexander cell. The Alexander cell certainly displays the effect of all of these features on the corrosion reaction and is therefore the only known method of short-term monitoring for electronic corrosion control. Other interference possibilities. The generation of AC electricity by mechanical means requires that energy is applied to rotating magnets which induce a potential into coils of conductor wire. These coils discharge current through carbon brushes into cables that are then at a higher electrical potential than the metal to which they are connected. The magnet then charges the next coil in turn, and the first returns to its basic potential value. In countries such as the UK, generating companies are required by law to supply electrical energy at exactly 50 cycles per second. This means that each conductor is charged and discharges its energy 50 times per second. The amount of energy carried by each conductor depends on how far apart the potential of each conductor is forced away from zero by the engine, mechanical engine, supplying the energy. For a 50th of a second, this is DC charge. There is then a mechanical arrangement that forces the current to flow in the other direction until the cable is charged negatively in relation to the original zero. The whole generator system is balanced to maintain the zero at an equal potential to the ground on which the generator is based. Field generators are sometimes unbalanced and cause potential of the ground to alter. This can be manifest as a steady fixed potential increase or decrease, which can be plotted around the earthing system of the generator itself, or it can be in a waveform that effects of which can be detected up to half a mile away in high resistance ground. Overhead high energy conductors, high tension wires, operate in the UK at a potential difference of up to 400,000 volts. These are referred to as kVA, and have a field of influence that can affect buried pipelines that run parallel to them. This can be seen in fluctuations in the voltage measured in pipe-to-soil surveys. In one such instance, voltage on the meter swung from 0.600 millivolts to 2.13 volts in an irregular pattern over a period of 20 minutes. This was in a location where 3 pipelines ran parallel to 2 high-tension pylons rated at 400,000 and 232,000 volts respectively for lengths of several miles. I reported this matter to the operators of the pipelines, but learned that sections of each of the pipelines had to be replaced as they took no action on my advice. I was able to offer assistance in this matter. I was unable to offer assistance in this matter as I had no money to set up a business. I was shut out in the cold by established service companies despite a letter from the chief executive of one of the operators instructing that my services be engaged. So that was something that could have been prevented, cost millions of pounds, and the pipeline suffered because they didn't take my advice. Right, basic interference testing and resolution. The first step is to acquire all available drawings and maps of the area. Local planning authorities, electricity suppliers, gas and water suppliers, and the National Survey authorities are useful starting points. Satellite imaging is now a valuable resource to give factual picture of which to base all the information in the absence of the dynamic project which incorporates all of this information. The second step is to add all the historical data available from cathodic potential records to a schematic of the area in which the form of a circuit diagram. The areas of high ground should be shaded in various degrees of green, allowing for areas in which the corrosion might be found should be shaded in various degrees of red. It is convenient to relate all of these voltages to the pipeline metal being 0, which is coloured in deep red. All of this is in the pictures which are together with this module. It follows that a grounded area of 5 volts or more would be deep green, and that any metal in this area would be protected by the current tending to enter at every interface. This metal would then be charged as shown as an equal voltage to the part of the ground bed profile through which it passed. If this is the subject pipeline, it would immediately drain of charges by the negative connection to the transformer rectifier, thus being at 0 volts. Any sacrificial anodes attached to the subject pipeline in the area of influence of the impressed current ground bed would be protected depending on its stability in relation to the pipeline metal. It is important to recognise that in an area of over 1.6 volts, the ground potential would show a depression in the potential with the impressed current switched on, and this would reverse to a peak when the current is off. This feature is easily recognised in a 2 half-cell survey grid plot with the TR switching. A foreign conductor passing through the subject ground bed area, very green, will pick up charges and discharge in areas where the ground bed potential is lower, shaded red. Their presence will cause the ground potential to be higher, greener or less red than the surrounding ground. This will be detectable on CIPS or DCVG surveys, but the cause may not be apparent until a proper 2 half survey is conducted with that particular ground bed switching. It is best practice to notify all services in the area of interference testing and to invite their representation. However, it is never essential to have their cooperation, which is just as well, because you will find that most of the time they have no idea what it's all about. Even worse is that some of them pretend to know what they are doing, but the procedures are not logical and are unproductive. Don't let them confuse you. Keep a clear electrical picture in your head based on the data that you gather. Believe your meters and trust your own expertise. Electricity does bullshit. If you haven't established all the facts, then your electrical picture will be unclear. Gather more facts. Add data to the schematic circuit and a real picture will become clear. If you could get the cooperation of other operators in the area, then it would be very useful to get them to switch their equipment at certain stages of your investigation. You should only do this when you want to confirm your own picture and can predict the likely outcome of their switching. You should explain your reasoning to them before the switching begins. If the results are not as expected, you will then look a fool if you do not have alternative paths of inquiry. So make sure you have covered everything. At this stage, you should have remedial action in mind.